To work out the resistance of a conductor, we need to know the first three factors of a conductor's resistance. Those three factors, just go over again, is N for material, and they'll be given as the figure row, and that's going to vary depending on what the conductor is, whether it's copper, aluminium, silver, gold. They'll all have different figures there, because as we change our material, our resistance changes. The next one's the area, and that's given as meters squared. So when we buy a cable, when we buy it, we'll be buying a cable, we know the cross-sectional area, how fat the cable is, and that's given to us as millimeters squared, and we've got to convert that to meters squared, and we'll look at that in a minute. And the last one's the length, how long the cable is. The longer it is, the more resistance it's going to be. So these three factors is going to affect the cable's resistance. Temperature, we know, also affects the resistance, but we're going to look at that in a different formula later on. So we're just going to concentrate on the material, type of material is, cross-sectional area of the cable, how fat it is, and the length, how long it is. This is the formula we're going to use. We've got R to work out our cable resistance equals rho, which is going to depend type of material it is, times the length in meters, divided by the area, which we've got to convert to meters squared. So resistance equals rho, the resistivity of the material, times the length in meters divided by the area, which is going to be meters squared. Let's look at a question. What is the resistance of 23 meters of 4 millimeters squared copper? So this one here, we know our length. Our length has been given to us there. There's our length. We know our area, and it's copper cable. So copper, we know rho. So there's our area, 4 millimeters squared. There's our length, 23 meters, and there's our rho, copper. And I know, because we can look it up on a table, that the rho of copper equals 1.72 by 10 to the negative 8. We can put this in, this information into our formula. So R equals rho 1.72 by 10 to the negative 8 times the length, 23 meters, and we can divide the whole thing by its cross-sectional area, which is 4.0 by 10 to the negative 6 meters squared. Let's just look at that last number now. In our formula, length is given as meters, so we have to be providing the length in meters, which we did, 23 meters, and area is also given as meters squared. Unfortunately, by cable, cable is quite small in its cross-sectional area, so when we buy it, we get it in millimeters squared. It's quoted as millimeters squared, and that's the information we're given. We have to convert the millimeters squared to meters squared to put in this formula, to meters squared, and I've converted that by putting a factor of by 10 to the negative 6, because 4 millimeters is very small when it comes to meters squared, and we're just going to have a look at that now. If I had a square 1 meter by 1 meter, that would be 1 meter squared, 1 meter by 1 meter. So all four sides are 1 meters. So this side here, between here and here, if it's 1 meter, there's actually 1,000 millimeters in there. 1 meter equals 1,000 millimeters, and over here there's also 1,000 millimeters between here and here. And we could turn that into drawing lots of lines that way, and lots of lines that way, 1,000 that way and 1,000 that way. We'd wind up with this big grid of all the individual millimeters squared. And right down here is 1 millimeter squared. So that's 1 millimeter up by 1 millimeter out. And how many of them will be in this square here? It's going to be 1,000 that way and 1,000 that way. So it's going to be 1,000 times 1,000, which equals 1 million. Or 1, 2, 3, 4, 5, 6. So that means that 1 millimeter squared equals 1/1,000,000th of a meter squared. So 1 millimeter squared is a very small fraction of a meter squared. So therefore we can call 1/1,000,000th 0.000001. It's the same number, 1/1,000,000th or 0.0001, or we can call that 10 to the negative 6. 10 to the negative 6, 0.0001, or 1/1,000,000th. All the same number. So therefore, if we got 4 millimeters squared up here, 4 millimeters squared, it becomes 4 by 10 to the negative 6 meters squared. So we're converting millimeters squared to meters squared, and it shrinks it right down by a very, very big factor. Let's go back to our formula. 1.72 by 10 to the negative 8 times 23 meters divided by 4 by 10 to the negative 6 meters squared. You can put that straight in your calculator. Let's look at doing that. Here it is here. So it was, I forgot my number. Let's go back and have a look. So I would put a bracket in first. I'd go bracket, and I go 1.72 exp negative 8 times 23, close the bracket, divided by the area, which is 4.0 exp negative 6 equals, and you'll get your answer. This equals 0.0989 ohms. So it's about 1/10 of an ohm. The other thing we can do is, when we've got our formula here like this, we can do a bit of a cancelling. 10 to the negative 6, and take that off, and that changes to negative 2, and then we could put a 0.23 there, and then that gets rid of that altogether. So it would be 1.72 times 0.23 divided by 4, and you'll get the same answer.